Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. You know, if you've ever just paused, looked around at the world, and wondered how or why things happen, you are in the exact right place. Today, we're embarking on a journey into the mechanics of how we actually understand our universe. We're going to break down the very foundation of science. And I don't mean a dusty collection of facts you just memorize. We're talking about a dynamic, living process of discovery. We're going to see exactly how you can use these tools to make sense of the world.
All right, let's look at our roadmap for today. We'll start with 1, the core of science. Then 2, giants of scientific history. Next is 3, the process of inquiry, followed by 4, making a testable hypothesis. And we'll wrap up with 5, collecting and analyzing data. Let's get right into it.
Section 1, the core of science, the study of how things work.
I want you to think about this right from your own perspective as a student of the everyday world. Imagine a roaring campfire or a cat just leaping effortlessly through the air. Now ask yourself some everyday questions. What exactly makes that fire so hot? What are the 3 things that actually need to be there to make it burn? Or think about the cat. How in the world does it generate enough force to jump that high? What muscles is it even using? These aren't just random shower thoughts. These are the exact kind of phenomena that spark real scientific curiosity. Science always starts with just observing these everyday events and wanting to explain them.
So the absolutely crucial point here is that science is simply the study of how things work. It's not some rigid textbook. It's really divided into 2 main parts, the knowledge we've already figured out and the active process, the scientific inquiry that we use to find out even more. It's an ongoing, dynamic exploration.
And because our universe is, well, massively complicated, science is a huge subject. So we break it down into specific areas of study. You've got biology for living things, physics for energy and forces, which totally explains our jumping cat, by the way. Then there's chemistry for studying matter, geology mapping out the Earth's structure, astronomy looking way out into space, and meteorology studying the weather. Honestly, no matter what part of the universe you're curious about, there is a branch of science dedicated to figuring it out.
Section 2, giants of scientific history, the people who helped us get here.
See, when you practice science, you aren't doing it alone. You are joining a grand collaborative legacy of mentors and pioneers who paved the way. Take Marie Curie, for example. She's an absolute historical giant. Her immense curiosity and perseverance led to groundbreaking achievements. Her work directly contributed to developing the X-ray and actual treatments for cancer. She really showed us that a deep desire to learn can literally change the world and save lives.
And that knowledge ripples outward. Enter Rosalind Franklin. Her work totally transformed our knowledge of DNA. And guess what? She used X-rays to do it. This is such a beautiful example of how scientists do not work in a bubble. The discoveries of one scientist, like Curie's work with X-rays, are built upon by later scientists like Franklin. It allows our collective knowledge to constantly grow. It's just a massive, multi-generational team effort.
Section 3, the process of inquiry. Simply put, how we do science.
Now, to join this team, you can't just guess. You need a solid system. Step 1, ask a question and make a hypothesis. Step 2, identify your control and independent variables. Step 3, decide exactly what you're going to observe or measure. Step 4, choose the right materials or equipment for the job. And finally, Step 5, decide how you'll analyze that data to see if your hypothesis was actually correct. This right here is the ultimate blueprint for discovery.
Section 4. Making a testable hypothesis, an explanation of phenomena.
Here's the catch. Your hypothesis absolutely must be testable. Look at the difference here. Plants grow faster under blue light than red light. That is totally testable. Why? Because we can actually run an experiment. We can grow plants under both lights and just measure their heights with a ruler. Now think about the alternative. Plants are happier growing under blue light. Well, that's completely untestable. We can't scientifically measure a plant's feelings, right? You always need a statement that you can prove or disprove with real evidence.
And to test that hypothesis, you really have to understand variables. The independent variable is the thing we alter in an experiment. The dependent variable is what changes because of what we altered. Think of it like making pasta and heating water on a stove. The amount of time you leave the burner on, that's the independent variable. You control that. The temperature the water actually reaches is the dependent variable, because that temperature depends entirely on how long you heated it. Keep those straight, and your experiments will always make sense.
Section 5. Collecting and analyzing data. Ensuring accurate measurements.
So when you're finally running your experiment, you're gathering data. And there are two main ways to do this. Qualitative observations mean using your 5 senses to notice things, like seeing a liquid change color or smelling smoke. But honestly, in science, we usually need something a bit more exact. That's where quantitative measurements come in. This means using specific instruments to get hard numbers. You'd use a thermometer for exact temperature, a microscope for tiny objects, or a digital stopwatch for precise time. This instrument data is what truly helps prove your hypothesis.
Now, when you're taking those quantitative measurements, you need two things: accuracy and precision. They might sound like the exact same thing, but actually, scratch that, they are critically different. An accurate measurement means it's super close to the real value. A precise measurement means your results are grouped really close together when you repeat the test the same way, proving they're reliable. You absolutely need your data to be both accurate and precise if you want to draw a conclusion that other scientists are actually going to trust.
So why do we do all of this? Why the hypotheses, the variables, the endless measuring? Well, because this exact scientific method scales up to create massive real-world solutions. Take a look at solar panels. Scientists use this exact process of inquiry to figure out how to generate electricity using just the energy from the sun, helping us ditch fossil fuels. They're even developing this amazing thing called agrovoltaics, which is putting these solar panels alongside crops to lower the farm's water needs and fight global climate change. Science isn't just about passing a test. It's quite literally about solving the biggest challenges facing our Earth.
Which brings us to the end of our explainer. But before you go, I want to leave you with a direct challenge. Look around your own neighborhood, just like we did with the fire and the cat at the very beginning. Think about the issues you see every day. How can science, this active process of asking questions, making testable hypotheses, and analyzing real data, be applied in your community to solve a problem? The tools are in your hands now. It's up to you to start investigating. Thanks so much for learning with me today, and keep asking those questions.